speaker for today is Shuman Banerjee. He works with Dr. Melanie Moses and in the ScaleNet lab. Please help me welcome Shuman.
Good morning, everyone. I'm going to help you switch gears to molecular biology now. My talk is going to be on modular radar. It's an immune-inspired strategy for distributed systems. Distributed systems are the in thing. They are being used in environmental monitoring, disaster relief, military operations, multi-rover control, intrusion detection systems, anti-aircraft systems. Most of them, physical space is really important. They're also resource constrained, either power or bandwidth, or both of them, and we really care about scalability. Very surprisingly, the natural immune system also operates under the same constraints of physical space. There are constraints of resource, so the amount of metabolic input that you can have into the natural immune system, the number of immune system cells that you can have to fight a pathogen, and performance scalability is a real concern too. So I'm going to draw your attention to this cutout mouse and this horse to get an impression of how things scale in the immune system. Only a few immune system cells can actually respond to a pathogen, like 1 in a million. So as you go from a mouse to a horse, this search problem for a pathogen becomes much more harder. Then there's a very hard search problem. So these immune system cells, these very rare immune system cells, have to search for localized pathogens. So the search problem within this mouse and this horse, the natural immune system of a horse has to search throughout the physical space of this body, which is a much harder search problem. And then there's a response problem. The natural immune system has to produce antibodies to actually knock out these pathogens, and these antibodies are getting diluted in blood. So this horse has more blood than this mouse, and hence the natural immune system of this horse has to produce more absolute quantities of antibodies than the natural immune system of a mouse. And to add to the surprise, we see nearly scaling gradient search in this mouse. So the natural immune system of a horse and the natural immune system of a mouse search and respond to a pathogen, in our case West Nile virus, in more or less the same time, 3 to 4 days. So the immune system is doing something really miraculous. It's found out a way of reducing this search space. So how does it do that? And the solution is to have these fantastic anatomical structures called lymph nodes. They are a place in which immune system cells and pathogens can actually encounter each other in a very small volume of tissue, and they form this amazing decentralized detection network throughout our body. It's like having these detectors, just like other sensors. And so search is now modular, so it's divided into each of these modules, these small nodes which you can barely see. It's efficient within those modules, and it's a distributed parallelized process. And we call this a modular radar search and response. Radar for robust, adaptive, decentralized search and automated response. So what's going on within the lymph node? So if this is our lymph node, there are these immune system cells which try to detect these pathogens, and as soon as they find these pathogens, they immediately migrate to the nearest neighboring lymph node. So there is some time which it takes for them to actually do that. And then once they're within the lymph node, they actually present these pathogens to some other immune system cell. They say that, do you recognize this pathogen? This is what I have had. Mind you, there are 1 in a million of these within these lymph nodes, so it's a very, very hard search process. So that's all the local communication which is going on within this lymph node and around it. And there is a global communication piece. So once this immune system cell recognizes this pathogen, it starts proliferating like crazy. And then it starts recruiting other immune system cells from other lymph nodes, and This is a search through a physical space, so it takes time to actually physically traffic these immune system cells. So we have local communication going on within and around the lymph node, and we have a global communication piece for actually recruiting other immune system cells and physically trafficking them over large distances. So if I were to design a system of these lymph nodes, how would I actually do that? So some of this is our whole body, and what I could do is I could have a field of very large lymph nodes, and what that would do is, suppose this is the infected site lymph node, it has to communicate with fewer other lymph nodes. So it reduces the global communication time. But now, there are fewer of these lymph nodes. So a single lymph node is now passed or has to service a larger volume of tissue, which means that these guys have to travel now over larger distances. So what it gains in global communication time, it loses in local communication. I could do something else. I could have lots of these small lymph nodes. So it means that now this guy has to communicate with more of the others. So it increases global communication. But now, since there are more of these guys, each lymph node is in charge of a smaller volume of tissue, which means that this immune system cell has to now move over a smaller distance. So this architecture reduces local communication time at the cost of global communication. Well, obviously the optimal architecture is to balance these two, and we call this sub-modular architecture. So as the size of the organism grows, we have more of these lymph nodes. This one has 3 here, this one has 5 here. So having more lymph nodes means that each lymph node is in charge of a smaller volume of tissue. It reduces the local communication time. And then these lymph nodes are also getting larger. So it means that if this lymph node is getting larger, there are fewer other lymph nodes that it has to communicate with. So this kind of an architecture actually balances local and global communication time. And again, we call this a sub-modular architecture. So the total time to search and respond is, of course, the sum of the local and global communication times. As I said, the local communication time is composed of the detection times around the lymph node, the migration times, and the time within a lymph node. And the global communication time is merely the time taken to recruit these immune system cells over larger distances. And in previous work, we actually did explicit minimization. And what we found is that the number of lymph nodes actually increases with the size or the mass of the organism raised to the power 4/7. That's the number of lymph nodes, and VLM, which is the volume of the lymph node, or the size of the lymph node, increases as the body mass raised to the power 3/7. So this explicit minimization tells us that the number of lymph nodes and their size should increase in a specified way with the mass of the organism. This is a qualitative agreement with data we have from mice and horses and elephants. However, I should caveat this with the fact that we don't have too much data. We really need much more data to have better confidence intervals. So to summarize this part, there are increasing costs to global communication as organisms are growing bigger, and the immune system has come up with this great way of balancing local communication, which is detecting pathogens, and global communication, which is recruiting immune system cells using the sub-modular architecture. And our idea was to take inspiration from this and see if we could get some nice results in distributed systems. So in this talk, I'm just going to talk about peer-to-peer systems, which are used to provide distributed services like search, content, and administration. In this setup, computer nodes store data or service, and of course, no single node has complete information about the whole system. And the idea is to use decentralized search using only local information to find the data or service that you are interested in. We're going to look at a specific peer-to-peer overlay network called Semantic Small World, SSW, which represents objects by a collection of attribute values derived from object content or metadata. It aggregates data objects with similar semantics close to each other in clusters so as to produce decentralized search times. So this is a diagram of a system. Here we have 4 clusters, and each cluster has 3 nodes within them. And what it does is, there is local communication within these clusters by neighbor flag. So each node transmits a search packet to all its connected neighbors. And then there's something very unique in the system. It does global communication in a very unique way. It makes the network of connections between these clusters a small node. So there is this long distance connection, which is a thick arrow over here, and there is these long distance connections obeying a precise probability distribution. And there was work by John Klein showing that if you have these long distance connections obeying a precise probability distribution, you can have very efficient decentralized search. So you have local communication by name of flooding, and you have global communication by following these long distance hops and these short distance connections. And what the authors of this system found was that the global communication time, which is the time to actually send So these authors found that the time for global search, that is the time to propagate these search messages across clusters, is given by O of log squared n by c over L, where n is the total number of nodes in the system, c is the number of nodes in a cluster, and L is the number of long distance connections each node can have. So yeah. So our contribution was twofold. We varied the cluster size. So our contribution was to vary the cluster size and vary the number of long distance connections as the logarithm of the number of clusters. It's a slow growing function. And what we're doing is we're saying that each node will have O of log n over c, where n over c is the number of clusters, number of connections to long distance connections to its neighbors. And now the global search time reduces to O of log n over c. And this is a densification property, so such densification properties are an emerging property of technological networks shown by John Glenville's group some years back. And what it does is it also incorporates these redundant search pathways throughout the network. So now the time to actually traffic a message is the sum of the local communication time and the global communication time. And as I said, the local communication proceeds by name of flooding. So if you have the lattice of C elements, the worst case time taken to propagate that message is along a diagonal, giving us this square root of C term, the C elements. And the global communication time now becomes log n over C. And as you can see over here, increasing the size of a cluster increases the local communication time, but decreases the global communication time. And when we did explicit minimization, I left out the math out of all this. We get C is equal to O of log squared n, which means that the size of a cluster has to increase with the number of nodes in a system, or increase as a function of the system size. And that gives us a total decentralized search time of O of log n minus log n. So what does it mean now? How the system look like? So suppose you have a small system with 12 nodes, and you have a bigger system with 25 nodes. What it means is that the number of clusters has to increase. So there are 4 clusters here, and there are 5 clusters here. And the size of each cluster now also has to increase. This cluster has 3 nodes, whereas this has 5 nodes. What it means to have more clusters is that each cluster is now in charge of a smaller amount of nodes, so it reduces local communication time. And what it means to have a larger cluster is a cluster size which increases with system size is that it reduces the total number of clusters, hence reducing the global communication time. So that is the intuition behind it. And this architecture really balances these two, the tension between the local and global communication time, and this is what we came out of it. So similar trade-offs could exist in intrusion detection systems, multi-row control applications, wireless sensor networks. So that's there for future work. And just to summarize very quickly, the immune system and distributed systems